Alrighty, guys. Today we're looking at angular momentum conservation. First, we're going to look at a collision that causes rotation, and then we're going to revisit Kepler's second law that we did all the way back when we did universal gravitation. So, starting here with a typical AP type problem, we have a beam of mass m and length L with a frictionless pivot at one end that is held horizontally. The beam is released from rest and strikes a stationary ball of mass little m when the beam is in the vertical position as shown in the figure below. The beam immediately stops upon striking the ball. Determine the speed of the ball just after being struck by the beam. So there's a lot going on here. There's a progression of images and topics that we need to look at, and I have the diagrams below of I'd say the three most important positions of the beam. So number one is right before the beam, or right at the moment the beam is released, it's in the horizontal position. And then just before striking the ball, the beam is in the vertical position, but it's rotating. So it has an angular velocity that I'm going to call omega. And then just after the beam strikes the ball, where the ball moves off horizontally and the beam comes to a complete stop. So what I'd like to do during the transition between each image is go through my LEPs, go through my angular momentum, energy, and linear momentum, and decide what's going to be conserved, so what conservation law would be appropriate. I also know the moment of inertia of the beam is 1/3 ml squared, because it's like a rod or a beam rotated around its end. For each of these images, I'd like to draw a torque diagram. So I'll put the forces where they act. So of course, at the center of the beam, I have the force of gravity, or big M G. And I'm going to have that in each case, the force of gravity straight down and the force of gravity straight down. Okay. So I want to first establish a pivot. And I think for anything that's actually rotating, it makes all the sense in the world to put the pivot at the rotation axis, and then measure the torques around that axis. So, of course, there is something holding the beam up. You could call it like a normal force at the pivot. I'm not really worried about it because it doesn't contribute to a torque, because it's applied right at the rotation axis. So the first thing I'm seeing is, in this orientation, when the beam is in a horizontal position, the force of gravity is causing a torque. The force of gravity has a lever arm, or a distance perpendicular to the pivot. So the force of gravity is causing a torque. That actually means that angular momentum is not going to be conserved in this orientation. The other thing I'm noticing is, in all of these pictures, I have a fixed axis. And anytime you pin an object down and you have a fixed point, we know linear momentum's not going to be conserved because the beam is not allowed to translate. So that fixed axis keeps the beam from translating. So I'm going to eliminate linear momentum in both of these transitions as well. Energy would be messed up by things like kinetic friction, or what I have happening here is I have the picture of the rod just before striking the ball and just after striking the ball. So because there's a collision there, I'm assuming energy is not conserved in that transition, because they haven't said anything about the collision being elastic. And it's very unlikely that this collision would be elastic. So energy is not going to be conserved during the collision. And what I'm left with is, in the beam rotating downward from the horizontal position to the vertical position, it looks like only energy would be conserved, because this is prior to the collision. So I don't have to worry about losing energy due to the collision. So what I have in the first transition is conservation of mechanical energy. I have the beam starting out with gravitational potential energy in this orientation. And then in the second orientation, I have just kinetic energy. And since the beam isn't translating, that's just rotational kinetic energy, 1/2 I omega squared. Okay. What is interesting, and I think what we need to make note of here, is anytime the force of gravity acts as a torque on an object, then angular momentum's not going to be conserved. So for, let's say, for example, my pen, if I were to just spin my pen and throw it up into the air like that, well, because it's rotating around its center of mass and the force of gravity is applied to the center of mass, then the force of gravity is not causing a torque. But anytime that an object is rotated about an axis that's not at the center of mass, then we need to keep an eye on the force of gravity. And the force of gravity could very well be causing a torque, except when the object is in the vertical orientation. So what I'm seeing here in the second picture is that the force of gravity is straight down and the distance to the pivot is also straight down. So there's no part of the force that's perpendicular to that R. So in this orientation, as long as the beam is vertical, there's no external torque. The force of gravity is not causing a torque because it doesn't have a perpendicular lever arm. So we can use angular momentum during the collision, right? There is a force that slows down the beam, right? And that's going to cause a torque that slows it down. But there's also a force from the beam that causes the ball to speed up. And the good thing is that's an internal third law pair. The force of the beam on the ball and the force of the ball on the beam are equal and opposite. So I'd expect angular momentum to be conserved in this transition, but angular momentum is not conserved as the beam falls because the force of gravity is causing a torque. So let's determine what that angular speed is of the beam just before colliding by using conservation of energy. So initially, the beam has only gravitational potential energy. So I would call that like an mgh. And that's going to be equal to the rotational kinetic energy that the beam has in its vertical orientation just before striking the ball. Okay. Now, this H is illegal, and so is omega because they weren't defined in the problem. So right now they don't represent numbers the way that M, L, and little m do. So all of my answers need to be written in terms of big M, big L, little m, or G, or any other constants like that. So I'm going to go ahead and try to take care of this height. When I talk about gravitational potential energy, I know that I need a reference level. I need to be able to compare how high was the center of mass raised above some reference level. So what I'll choose as the reference level is going to be the location of the center of mass later on when the beam's in its vertical position. So I know that from the first position to the vertical, the center of mass has been lowered by a distance of L over 2 because the center of mass is located in the middle of the beam. So that height then is just L over 2. And I could also replace the moment of inertia with 1/3 ml squared. That's the moment of inertia of a rod or a beam around its end. And then I'm trying to get an expression for omega in all legal terms, just m's and l's and g's. So I'm going to go ahead and simplify this a little bit. I've got an mgl over 2. 1/2 and 1/3 is 1/6. I see an m on both sides. I'd be comfortable canceling those out. And then I have an L on the left and an L squared on the right. So that's going to cancel with just one of those. So if I were to simplify this, I would take the 1/6 and I'll multiply 6 to the other side. So that's 6G over 2 that's also left over. And that should be equal to, let's see, I also need to bring over the L by dividing by L, and that's equal to omega squared. I can simplify that a little bit. 6G over 2L is just 3G over L. And then to get omega by itself, I would take the square root. So the square root of 3G over L is the angular speed of the beam just before striking the ball. So that's 3G over L and then square root. So now that I have the angular speed of the beam just before striking the ball, now I can go to the next transition. And in this part, we have a collision taking place. So we're not going to use energy. We're not going to use linear momentum because of the fixed point. We're going to use just angular momentum. And prior to the collision, the angular momentum is just due to the rotating rod. So I would want to track angular momentum there as I omega, right? Any object rotating around an internal axis, I like to do I omega. However, after the collision, where again, I expect the angular momentum to be conserved, after the collision, the rod or the beam comes to a stop. So it's no longer rotating. And then we just have the ball that travels off horizontally in this direction. So that is now a translating object, but it's translating in a way that it's not, the velocity is not just collinear with the distance to the pivot, right? The velocity has a component perpendicular to the distance to the pivot. And the distance to the pivot would just be the total length of the beam. Okay. So instead of doing I omega after the collision, I would do my R perp P or RP perp, right? And that is from the other way of writing angular momentum. For a translating object, it's easier to track it this way rather than doing I omega, since it's not really rotating. It's just translating in a way that it's not heading directly towards or away from the pivot. Okay, so for the angular momentum before the collision, we have a 1/3 big ML squared is the moment of inertia. We have our angular velocity that we found in the first part, so that's root 3g over big L. And then for the ball, as it moves away from the beam, the linear momentum is little mv. That's the velocity that we're trying to find. And then we need to know what part of R is perpendicular to the momentum. And the part of R that's perpendicular to the momentum is just the entire length of the beam. And that's based on where the beam struck the ball, right? If the ball would have been higher when it was struck, then that R perpendicular would be different. But based on this picture, the beam strikes the ball right here at the end of the rod. So R perpendicular is just L. And now to get V all by itself, I would divide by L and divide by little m. So I see that this L would cancel with one of those. So I have 1/3 big M L. I also need to divide by the little mass, m, and then root 3g over L. And that's equal to the velocity or the speed of the ball. Now, I could try to simplify that a little bit. And if you look at scoring guides online, they're going to be simplified a little bit further than this. You don't have to do that. And you take the risk of making a mistake if you try to simplify this out a little bit further. I'm going to go ahead and show you how you could simplify it if you wanted to. Where I have an L on the outside of the square root, L is the same thing as square root of L squared. So I'm going to rewrite that L by pulling in an L squared under the square root. And then I could do the same thing with this 3 on the bottom. I could, 3 is the same thing as the square root of 9. So I could put a 9 in here. So that's going to look like this. I have the ratio of the masses there, big M and little m. I am inside of the square root. I'm going to put L squared to take care of that L to the first power. I've got 3g in the numerator. I'm bringing in this 3 into the square root, so I would put a 9 there. And then I have that L on the bottom. So if I wanted to simplify this out, that L squared, one of those would cancel with the L on the bottom. I could also say 3/9 is 1/3. And this looks like the ratio of the masses times the square root of GL over 3. Okay? So one thing I'll do just to make myself comfortable and make sure I have something that is most likely the correct answer, I'll check the units out real quick. I need to get meters per second. I've got a kilogram and a kilogram. Those are canceling. I've got meters and meter per second squared. So when I multiply that together, I'm going to have a meter squared per second squared. And then under the square root, that's going to give me my meter per second. So it gives me confidence that this is the correct result because the units check out. Okay, so that was probably one of the more challenging problems that you could see on the exam, but it's important that with each step, we go through our LEPs and we go through those conservation laws and determine which one would be most appropriate. So we used energy to get the beam from the horizontal position to the vertical position, and then we used angular momentum through the collision. I've seen problems that would even follow up where if the beam doesn't stop, maybe the beam continues to swing forward. And that would all depend on the mechanics of the collision and the materials that are involved. If the beam continued to swing up, and they wanted us to predict how high it swings, maybe based on the velocity of the ball or something, then we could start using energy again, right? What messed up energy in this transition was the collision itself. So anytime that collision is happening, if it's not elastic, we can't use energy. But I've seen a follow-up question where we could go back to using energy to determine how high the beam swings or something like that. Okay, so you're going to want to go through that LEP with each process. Okay, the last thing I wanted to talk about, I do want to go back to Kepler's second law. And one thing we said about Kepler's second law was that in an orbit, like an elliptical orbit of a planet going around the sun or a moon going around a planet, we had said that the area swept out by a line connecting the sun to the planet, the area swept out by that line is constant for equal time intervals. And what we got from that was when the Earth is over here closer to the sun, it has to be traveling with a higher velocity. It has to be traveling faster here. And it's traveling slower over here where it's further from the sun. And we made qualitative arguments about being closer to the sun, you're in more danger of being pulled into the sun. Your gravitational force is larger. So you're going to have to travel faster to not get pulled into the sun. And that makes sense from a qualitative standpoint. But I do want to use a conservation law now really to prove that and determine why is it that we need to be traveling faster here when we're closer to the sun and we can go slower when we're further away. So I'd like to go through my LEP, my angular momentum, energy, and linear momentum for an object in an elliptical orbit, or really any orbit around some other big mass. The only force is the force of gravity. And the force of gravity is the net force on that object. So the one thing I'll point out is the momentum of that object is in the direction that it's traveling, and the net force on the object is not zero, so linear momentum is not going to be conserved. Right? We know that linear momentum is only conserved for an object if the external net force is zero. So force of gravity causing a net force, this object is accelerating, so the linear momentum is changing. Okay. As far as energy goes, we know energy is going to be conserved. Over here, I would say that I have a larger gravitational potential energy. So my kinetic energy is smaller. Over here, I would say that as I'm closer to the planet, I have a smaller gravitational potential energy, so a larger kinetic. So I could use conservation of energy to describe why you need to be traveling faster here when you're closer. But I don't love that relationship because we know that the gravitational potential energy is proportional to negative 1 over r. That's the distance to the middle of the sun. And then we know the kinetic energy is proportional to velocity squared. So that's a pretty complicated mathematical relationship where you have a v squared and you have a minus inverse r. And it's difficult for me to really predict what that velocity is going to be based on the distance to the sun. So I'm going to look at angular momentum here. And the one thing that I notice is that, yeah, there is a net force on this object. However, that net force is directly in line with what we would call r, the distance to the pivot, the distance to what you're rotating around. And since the force of gravity is in line with r, it has no component perpendicular to r, which means the sum of the torques is zero. So we have something happening here very similar to the ice skater. When the ice skater pulls their arms in and the sum of the torques is zero, but we still see their angular acceleration. We still see them start to spin faster. And that's exactly what's happening here. Angular momentum is conserved because the only force on the planet is in line with R. So there's no torque. However, if I were to look at angular momentum, which is I omega, out here where the planet is much further from the center of the sun, I is very large. And in order to conserve angular momentum, that means omega would have to be smaller in that position where it's further away. And then when the Earth is closer to the sun, it has a much smaller moment of inertia, which means in order to keep this product constant, it would have to have a much larger angular velocity. So that's the way I prefer to think about it when I look at planets and elliptical orbits. I consider the conservation of angular momentum because that's a little bit simpler relationship, being that it's linear, right? Moment of inertia is to the first power, and angular speed is to the first power. So I prefer that mathematical relationship. I feel like it's a little bit easier than the gravitational potential energy to kinetic energy relationship, which can be a little bit more cumbersome just to calculate. Okay, so that is it for angular momentum conservation. Thanks for watching.